Okay.
Great. Hi, my name is Jared. I'm a security researcher at Oak Ridge National Lab and a PhD student at the University of Tennessee, Knoxville. So is everyone here from this area? What do you guys do on a daily basis? Like, are you guys scientists, researchers, students? Is anyone here a student?
Yeah.
Like
at UTK.
At UT? Like a
SBA.
Okay. Is anyone else a business student? No. What's everybody do?
Software development.
Okay, software development. Anyone else software development? No? What do you guys do? Okay, well there's like 8 people here, so I just want to know what everyone does so I don't talk too much about the things I shouldn't. What do you do?
Industrial engineering, but I'm just a hobbyist.
Okay, great, that's awesome. Yeah, industrial engineering. Okay, great. And what do you do?
I'm business analyst.
Okay, great. Data scientist. Okay, so very much a mix. So we'll try and keep it. It might be a little too high level for some of you. It might be not high enough for others. I'll try and keep it right in the middle. So a little bit about me. Like I said, I'm a security researcher at Oak Ridge National Lab.
Are you sharing your screen?
Let's just check. Sorry. Should be. Oh, nope.
All right, cool.
There you go. Great. Does it look okay now?
Yeah.
Great. So again, I do security research at Oak Ridge National Lab. I lead 2 projects, one for the DHS and one for the Global Security Directorate there, and those revolve around cybersecurity for endpoints and power grid related systems. So a lot of that includes data science, and there's lots of reasons to know how to manipulate data in these systems as well. And I also am a PhD student at UT my first year, and I graduated from there with my BS last December with a computer science degree. I also teach data science, security, and DevOps at Treehouse, which is kind of like Pluralsight or Udemy or any of those other online platforms that you've seen. And then last, when I was an undergrad, I founded the Security Club and the annual hackathon, which most of the companies around here have been sponsors of in years past. And then finally, because you're in Knoxville, I go hiking. I feel like that's one of the redeeming qualities of this area. It's kept me from moving away to other places. So if you haven't gotten a chance to go to the mountains, please do it. Does anyone here hike? Anybody? Yeah, it's great.
Why reluctant backpacker?
Well, okay, so that one's funny because my friends forced me into going backpacking, and I like it only after I've started, but beforehand I absolutely hate it. Okay. So just the thought of going into the woods for like 3 days and having no access to anything modern, it's frustrating. But I do enjoy it, and I encourage you guys to do it as well. If I didn't put reluctant up here, my friends would harass me about me not being a real backpacker. So I'm going to start with saying that machine learning is hard, but in reality, theoretical machine learning is the hard thing. If you're going to develop algorithms for machine learning models, and you're going to build new models, build new algorithms, you are actually a doctorate. Someone has a doctorate and works for Google, publishing cutting-edge papers on this new method you've used to enhance the quality of your data by 50%. That kind of stuff is not easy at all, and it does require a lot of knowledge and background in data science, machine learning, math, computer science even. But the thing that's most successful for all of us is applied machine learning, and that's when you take these toolkits, like we'll talk about, like Scikit-Learn, and you just use their APIs, and you give it data that already exists, real-world data, and you make things with it. And that kind of machine learning is no different than writing code for a website or building an application to do any kind of thing. To know, and we'll talk more about that later, and I certainly don't discourage you knowing math. If you want to dive into this, you should. But at a high level, you can do this kind of stuff and get started and quench your thirst for doing machine learning without knowing in depth how all of it works. So again, to reiterate, you don't have to have a doctorate, and that's kind of just the driving thing that if you're going to outreach to people about machine learning, you need to stress is that it doesn't require an academic to do it. You don't have to have a doctorate to teach computers to learn new things, to predict the future, which you can do with machine learning. To create driverless cars, a lot of that is driven by machine learning in some rule-based systems. to identify early stage diseases. Often machine learning algorithms now are more effective than actual doctors at identifying whether some picture of a tumor or disease is actually, you know, some X or Y, and it can do it like 50 or 100 or however much better than real doctors because computers are way better at patterns.
Isn't that they're better or just faster?
They're just better at finding patterns. I mean, faster. So you think about, if you think about chess, and a human can only think so far ahead in chess. Now a computer can think way, way farther ahead. And now how that relates to machine learning is that machine learning can find way deeper patterns than a human can pick out. So fast to some extent, sure, but just being able to see a doctor seeing one picture, a computer seeing one picture, the computer can look at millions of examples in the past and say all of these point out this here, and the doctor only knows, you know, their experience in grad school or med school. Not to say that it replaces them. That's the last thing I want to suggest. It enhances, if anything, the doctor's ability to do their job. That's another thing you can get into with people is like, oh, AI is going to eat the world. I think it's going to be hundreds of years until, if ever, we're replaced by robots. I really don't think that's going to happen. As much as Elon Musk and all these people will scare you, I think it's complete garbage. It's a very divisive topic, so that's just my opinion. But what you do need to do machine learning, and at least what is very helpful, is having some programming experience because these tools do require it. And if you don't have that, then at least having a willingness to learn a little bit of programming. If you write any software, you're fine. Persistence is extremely important, and above all else, being curious about solving new problems. Because when if you're a data scientist, then the biggest thing that at least I've learned is that first of all, you can't stop looking at the data after you get frustrated that you haven't found anything. And second of all, you have to be really curious about, hey, let me check out this, or try and analyze it this way, or parse it this way, and keep trying to work at it until you solve the problem. And you'll be even better with machine learning if you have basic background in a lot of types of math. So statistics and probability, you really can't get away with that. If you want to do this more, it's helpful, very helpful to know that. There's some knowledge of optimization, so some machine learning algorithms use something called a gradient descent and boosting, and so they essentially just like optimize for the lowest error and other ways around that. Linear algebra is important. Just think of multiplying matrices because that's how you represent your data. Is if you're training on pictures of dogs and cats, the pictures are just going to be pixel values. So you just pass in, you know, a tuple of red, green, and blue into your algorithm, and that's all the computer sees is this matrix of pixel values. It doesn't see, you know, the colors in the same way we do. It just sees numbers. To know that if you really want to build stuff yourself. And then some complex software engineering experience is good if you want to kind of deploy these systems. So how does Python factor into this? Does anyone here write Python regularly? Most people, you guys?
Yeah.
Yeah, so everyone's like at least comfortable with Python. I'm not going to get any resentment about Python or anything. Okay, I'm used to speaking at KnoxPy and other Python related stuff. So anyone here done R? Yeah. Got the data scientist, and UT does a lot of R, yeah. So R, SQL, Python, all tools of the trade for doing data science. And I don't have to say that too many times. But just to convince you even more, Python's really easy to write. It's extremely readable. It stresses that at its core. It has a vast ecosystem. The batteries are included. It's their motto. They already have a lot of stuff for you. It's cross-platform, so you can write it and run it pretty much anywhere. And I like to say it can be used for major software projects, and that's very much the case. I mean, Google, Facebook, Twitter, all kinds of people use it for major projects. And people might tell you Python is a scripting language, but that is a lie. It might be a scripting language, but it's built huge things in the world. So it's not, you don't have to go and learn Java or C or C++ just to deploy your Python code. Or Microsoft. Don't learn that stuff. Don't learn C#. Nobody likes C#. Does anyone here write C#? We're lucky today, Alex.
Yeah, oh yeah.
Good thing this is recorded so everyone can hold me accountable. So Python is great for machine learning. There's lots of libraries, so we'll talk about Scikit-Learn today a bit. Anyone heard of TensorFlow before? Yeah, so TensorFlow is, so where Scikit-Learn is, you're given, you know, a nice, affordable Civic that will get you to your destination. Well, I have a Civic, so I'm making fun of my own car, not to make fun of it. But TensorFlow is you get the NASCAR race car, where it's insanely hard to work with in general. It's getting better, but you can do anything with it because it's at its root, it's a mathematical library to do machine learning-ish things. We won't get into that much today, but I think maybe someone else will come and give a talk on that later. Python, the interface and the data science libraries in Python is very similar to R. So if you're familiar with that, it's sort of familiar. And then there's lots of visualization tools. So we use a bit of Matplotlib today, which is a graphing library. There's others as well. So the last thing is everyone thinks Python is slow. Well, in data science and Python, everything's underlying is mostly written in C. The core libraries that Scikit-Learn built off of are called NumPy and SciPy, and those are all have C implementations underneath, so they run very fast. So machine learning, why does it matter and how does it work? So first of all, machine learning, I don't know, I'm trying to cover the high level, but I'll try and get through this quickly. So it's learning from data, little or a lot. Is anyone here just, how many people here are really familiar with machine learning already? So I'll probably keep it in the middle then because it seems kind of mixed up. So it can be used for making predictions. So that's things like predicting house prices. Deciding what something is this a dog or a cat? Is this a pedestrian or a stop sign? I don't want to hit a person, but I certainly am okay hitting a stop sign if it avoids hitting a person. Things, so Spotify, Apple Music, Netflix, all of those use machine learning. And identifying anomalies. So at least in my domain, security with anomaly detection. So given data on a network, can we tell you that this person is extracting sensitive data from our company and we need to find them and take their computer before they get out with it. And that's kind of anomaly detection. So why is this important? Like we talked about the pattern finding in medical devices and chess. So there's not enough people often to go through all of this data manually. And second of all, computers are a lot better at picking out patterns just because they can naturally recurse over lots of data more easily. And if you need any more explanation for that, then just check out problems that computers can solve it. They're much better than us at. So for example, Go, the game that was just beaten by an AI. To be fair, a lot of those things are very specialized to beat the players. But still the fact that human champion in that with a computer that's not doing anything other than flipping beds is pretty incredible. So how does it work? It's math. I have to touch that as much as we can, and we'll try and get into that. If you want to learn more about math, there's plenty of good places online. So I say if you need like college level stuff, Khan Academy is great. But if anyone has a bachelor's degree, they probably don't. But my recommendation there is just start with machine learning. Learn the APIs, and then as you see things you don't understand, Wikipedia is really great, and it's kind of confusing and it seems very confusing, but as you just dig into it, it's actually not too bad. But as developers, again, you don't have to touch most of that. But I'm not trying to say that to keep you away. If you're interested, please look at it. Because data scientists here tell you that you can't get away with doing what you're doing without knowing that. So there's a few major subcategories of machine learning. So when you hear a lot of people talk about this, they talk about supervised and unsupervised. Supervised is when you are given data that has labels. So this is a dog, this is a dog, this is a cat. Pictures of them, and we have a label with them. Then give it a picture of a mouse, and you want to say, oh, it's not a dog or a cat. So there's two things there. Classification is that where it's discrete bins of data. So you have you're identifying an exact thing. It's discrete in the sense that it's not a real number. Regression is when you're predicting a real number. So like you get house prices for Knoxville, and they're between the range of 80,000 and 100,000, all in that range with decimal places and everything. And you want to predict that a house in this neighborhood right here is worth $85,250. That is and 38 cents, whatever. That is a real number that isn't just can't just be categorized. So that's called regression. Unsupervised learning is when you don't have labels. So think of clustering. So if you get a bunch of unlabeled data, so think experiment results, and you have a bunch of just X, Y points, then you want to group them into clusters, and you do this through clustering algorithms, which we'll talk about. And there's also semi-supervised learning, which is essentially a mix of the two, but scientists figured out when you combine a lot of unlabeled data with a small amount of labeled data, not completely supervised learning, but also not completely unsupervised, that the data that came out that was clustered was a lot better. So that's what that is. And there's other parts of machine learning. So dimensionality reduction is important because if you have a problem that has 15 dimensions, and that dimensions could be, in the house example, how it could be the street that's on, the area code, the people around you, the size of the yard. Those are all dimensions to the data. And if you try and graph a 15-dimension thing in front of you, you're not going to even know what's going on. So there's algorithms to reduce the dimensions of your data and make it easier to reason about.
Do you lose, when you did reduce dimensions, predictive ability?
Yeah, so you certainly lose that, and I'm not an expert there in all the ins and outs there. But there's trade-offs to reducing it. In certain things, so for example, there's a good data set called the eigenfaces data set. If you want to classify, it basically the data set like presidential faces. So George Bush and actually Colin Powell and Reagan and others in the past. And it will give you the data as their faces, and you have to tie back new faces to those faces. And you actually do something called principal component analysis, which is a reduction of the dimensions by reducing the amount of fields you have coming in to a smaller amount and letting it classify them. As it turns out, in that case, you can actually do it with less features. So you do lose things sometimes, and it's just a way. It's just another method. Yeah, exactly. And that's why machine learning, it's a huge field, and honestly, it just takes a lot of experimentation. Reinforcement learning is if you think of a toddler that will try and crawl upstairs and keep bumping into walls or falling down and having to go around stuff. Essentially, what you do is you give the person a function to maximize for. And they say, hey, every time you don't do this, we're going to penalize you, we're going to reward you. So that's kind of how reinforcement learning works. And it's essentially, over time, you reward the algorithm for getting closer to the best possible solution. Learns to approximate that solution. So similar to that is genetic programming, where if you think of evolution, it's a genetic programming method, and you evolve something to do better than task over time. So if you've ever seen, has anyone seen that robot that Boston Dynamics has that if you kick it, it stands back up? I'll pull that up in a second, but it's essentially this little robot that if you try and kick it, it won't fall. It'll lean over, it'll pull itself back up. You can hit it with a car, you can do all kinds of things like that. And originally how it's trained is by using reinforcement learning and genetic algorithms to make it realize if it hits the ground, that's the worst possible case. So it needs to optimize for not hitting the ground. And so it will do everything it can. It'll make movements in a way that gets it closer to not hitting the ground. And that's what reinforcement learning is. So think back to psychology. If you're reinforcing positive behaviors, that's what you're doing here. Finally, structured predictions is, I think that's how Wikipedia worded it, but it's just probabilistic methods. I think it's what I came across, and things like just basic probabilistic models. So if something with some probability happens, then what's the probability something else happens? So those are the major subcategories of machine learning. There's plenty of others. So deep learning falls in here too. But honestly, deep learning is just neural networks that are very deep. I hate buzzwords, and that's just how it is. So first we'll talk about supervised learning. So essentially you take data with labels and you combine it with similar data, and that will output similar data with labels. So you train it on data that already has labels, and then you pass it data that hasn't seen before, and then it will label that data. And that's supervised because you're giving the algorithm things that tells it what exactly the data is. And that's different from something I'll talk about in a second. But we already talked about classification and regression. So classification is discrete subcategories, and regression is real values. So those are very important for different types of problems. So again, like the canonical example, picking cats or dogs, or picking whether someone's going to score between 0 and 100 in a test based on their past performance. That would be a regression. So unsupervised learning is taking data without labels and then getting unlabeled groupings of data. And the thing we'll talk about there is just clustering. And the most common algorithm for that is called k-means. So we'll talk about that in a second. Essentially, it just, at a high level, it just clusters your data around central points in those clusters. They're called centroids. And it uses a distance metric to group them together. So that's very helpful for things where you don't know the labels and you just want to put together some of the results. And it kind of gives you a sense to what the relationships are so that a human can come along and say, hey, this is what this is, this is what this is. We talked about semi-supervised, and again, to reiterate, that's when you have a large amount of data without labels plus a small amount of data with labels, and that gives you better unlabeled groupings of data. So what's the process of doing machine learning? It's actually pretty straightforward when you're just implementing it in Scikit-Learn. But just roughly, you want to get the data. First of all, those two words are a lot bigger than and a lot harder in many cases than you would think. To give an example, there's already plenty of data sets on like images with labels. But a while ago, I wanted to use a certain neural network to generate caricatures from people's pictures of themselves. But there's no good data set of people's pictures mapped to caricatures of those people. So there's no really way to use a neural network to translate between the two when you don't have the data set of original mappings. So that can be hard if you have a problem you want to solve and don't have the data. You have to get that data. So once you have the data, you need to pre-process the data, and this is where the cleaning and transforming, all of that happens. So if you have data in a way that there's lots of missing values, you want to strip those out, things like that, because the models are pretty sensitive to having messed up data. Visualize that model with existing data and fit and train that model. So we'll show that in the code that we in the demo. But you pick the model you want and you pass in the existing data and say, hey, learn from this data and build me an initial model. And then to test that model, you always want to test with data you haven't seen yet. Because if you test the model with data you already have seen, it's going to be very good at predicting those values, and that's what we call overfitting. And finally, you want to do stuff with that new data after you tested it, and that's what we just call predictions. So prediction, classification, all those kind of things. Does that make sense? That's straightforward. Yeah, we'll get into some code here in a second. So how to choose the right model or algorithm estimator, that's kind of a tricky thing. But upon request from KnoxDevs, if you're not KnoxDevs, join it, please, knoxdevs.com. There's a Slack channel, and I ask people what they want to see. And someone asked about the most common models for certain types of problems. So I picked a few here that I've seen mostly and are some of the bigger ones. So for classification, some of these are older and not nearly as avant-garde as people would think. But they're still used every day for all kinds of tasks. So for example, classification, there's something called a support vector machine, which I won't really get into details of how it works because I'll butcher it. But it's an older model from, I guess, the late 90s, early 2000s, and it's basically a type of approximation. There's a naive-Bayes classifier, which uses Bayes' theorem, which is a probabilistic theorem. That's one of the most straightforward ones. Decision tree I can actually explain, where it's essentially you start with your piece of data and you say, hey, is this red or blue? If red, go this way. If it's blue, go this way. If it's red, then is it round or square? If it's square, go this way. If it's round, go this way. And then you just break down to the very bottom. There are bins that it will predict out to. Random forest is sort of similar to decision trees, where it's it's a probabilistic model that's lots of different trees that are spread across. They're all randomly distributed. Stochastic gradient descent is another. I talked about optimization earlier. It's another type of approximation where it does a gradient descent. So if you think in calculus and you have a plane and you want to get down, you want to like descend that plane to the lowest point on some curve, then that's what that is. And I could be butchering all this math, but again, I'm not a mathematician, I'm a computer scientist. Neural networks. Anyone here know what neural networks are? Anyone heard of them? Yeah. So literally, all that is a really good way to approximate a function. So if you give a neural network and say, tell me whether this is like a 0 or 1, it's just a great way of connecting all these little nodes that can either be up or down, on or off. And we connect them in a way that they transmit data and they produce some magical number at the end. And neural networks with not many layers, meaning not many nodes in between the input and output parts, are pretty easy to reason about. But when you hear about deep learning, that's when you just stack layers and layers and layers together. And there's other types of special neural networks within there that we won't talk about. But that's where most of the breakthroughs have come through in the last few years. And honestly, the neural networks have been around since the 60s, and even, I think even before that. So they're not really a brand new field, but there has been a lot of recent exploration of new types of neural networks. So if you want to do research, look up convolutional neural networks and recurrent neural networks are some of the more recent ones. So regression, we talked about approximating real values. Linear regression is just ordinary least squares. It's just an approximation. So if you think of a bunch of dots on you think of an XY plane, and there's a bunch of dots on it, and you want to draw a line through it and linearly separate those groupings, that's what linear regression is. Ridge regression is another type of regression that's used a lot. Support vector machines can also be regressors in addition to being classifiers. And then the same with stochastic gradient descent neural networks. So these are some of the most common, and if you want to use them, then just literally pick up Scikit-Learn and start working with it. What's up?
Isn't logistic regression also one of the most commonly used?
Oh yeah, logistic regression too. Yeah, so yeah, they're all. If we go to, I can never get out of this window. Let's see. That's all I wanted, but I'll make this bigger in just a second. That's that up. Oh, too big. So yeah, if you just go to the regression, and they have all kinds of linear models here. So ordinary least squares, which is linear regression, ridge regression, the lasso model, all kinds of stuff. And they'll get down to yours, the regression is somewhere here. There we go. There we go. So it's funny because, again, its name, it says it's a logistic regression, but it's actually another linear model as well. So these are all different mathematical ways of approximating functions. And that's the only thing you have to think about. But when it actually comes down to using these models, it's extremely straightforward. And I'll show you in a second. We'll actually do it, but I don't want to jump too far ahead. Okay. And finally, clustering, k-means is the only one that I want to mention. For the most part, it's very simple, where you have a bunch of points in a graph, and you want to draw center points in groupings of data and measure the distance between those points, and then drag them in. I'm going to draw like a circle around them. And it's a great way for grouping together data you don't really know anything about.
So Scikit-Learn have libraries which.
Yeah, so it essentially has a Python class for every single one of these. And there's I don't know about hundreds, but tens of more for each of these things here. And not mentioned here is the dimensionality reduction, so like the principal component analysis like we use for eigenbases. Also not mentioned here, they have ways to essentially so in machine learning, you can apply whatever model you want to data, but another hard part is actually picking the right parameters for your model. So models are very configurable, and so for example, a neural network can have 2 layers or 1,000 layers. And there's a way in Python and Scikit-Learn to give this class like 10 models and say, hey, vary all these parameters automatically for me and tell me which parameters are the best fit for this model. And then it will tell you, without you having to try a bunch of graph, what's the best fit. So that, like we talked about when we talk about the process, picking a model and building it, generally my approach, and the general approach is just to take your data and apply as many models to it as you can and pick the one that gets the best results using a combination of training and test data.
That can take quite a while.
For certain tasks, yeah, but if you're building, driverless cars and you don't want to kill people, then you got to take a while to do it. But it's a process. It's a process, yeah. And also, I'm not the best at this. My research is security, but I use machine learning in my day-to-day. But data scientists and machine learning people specifically are a lot better at this because they've done it for years. But like I said, that's why persistence is key. And so another thing I actually heard the other day that's good, and I've done a few times before, is that if you're interested in doing this even more, rather than just going through the documentation like we'll do in a second and do some examples, go find the paper in modern machine learning. And if it's something interesting to you, take that paper and try and reproduce the results completely on your own and use like Python, Scikit-Learn to do it. And that way, without using their own code, you can reproduce results in a paper in some really big conference that just came out. And that will teach you how they went about doing it. And you can read their paper to use as instructions. but don't look at their code. And that's a good way to learn this stuff as well. Any questions so far? Okay. So Scikit-Learn, we talked about Python a bit. So first of all, Scikit-Learn makes machine learning a lot easier. It has a straightforward Python interface. It has APIs for classification, regression, clustering, all those things we talked about. And again, it uses C underneath to enable better performance. So data in Scikit-Learn is pretty, just like data in other Python data science libraries, use a library called NumPy, which is essentially a matrix library. And you can split training and testing data with certain built-in functions. Like I said, you don't want to test your data on data, your models and data that's already seen. In fact, at the end of the day, you just need to get the features and labels out of the data source you have. So you need to know that these are the different data points for this particular label. Or not labeled in the case of unsupervised. So another thing that Scikit-Learn abstracts away is estimators. And estimators are essentially the models and regressors and other things you would use. So these are the actual machine learning components that do the predictions and everything. And you can think of them as just being a class that has a function on them called fit, and that fit takes some data. So it takes data. So that's your features, and it takes y, which are the labels. Or if you don't have labels, then it doesn't take them. And the estimators are what they use to train the model, and then finally you'll predict on it as well. So the prediction interface is pretty straightforward. You just say, hey, I've got my model. I want to now pass you this set of features and tell me what label it should have. Or in the case of unsupervised, it doesn't. It just spits out what cluster I think it's in. And finally, another thing that's important is transformative data. So you might think about, you might want to normalize your data. You might want to take the average of your data. You might want to remove all the empty values. That's stuff that Scikit-Learn gives you functions to do as well. We won't talk about that much today, but I'll show you the API and where it is, and it's pretty straightforward. So this one's actually really fun. So what happens whenever you don't know, I'll zoom in a second, but when you don't know what model to use. So Scikit-Learn actually provides this really cool thing. So we'll start here. And if you have less than 50 samples, the recommendation is pretty straightforward to say to get more data, which is pretty, it's a small amount of samples, so you probably do want more data. So if you're predicting a category, then what you want to do is, if you're predicting a category, then you go here. And if you have label data, that's what we talk about, that's classification. So in that case, it just breaks down saying, hey, if you've got less than 100,000 samples, then you should try this model. If that doesn't work and it's text data, then try naive Bayes model. If that doesn't work, then try the k-neighbors classifier, which does nearest neighbors, things like that. You can follow that as well and say, hey, do I not have label data? But am I trying to predict the category? Then we'll use stuff like k-means and other clustering algorithms. Now, if you want to predict the quantity, if you want to predict the quantity, so again, like a price, something that's a real value, then we'll use regression. In that case, there's all kinds of regressions here. So this is stochastic gradient descent, a lasso, ridge regression, all kinds of things. And finally, if you're just looking around at your data, then you can use the dimensionality reduction. So that's, remember we said we don't want to graph something that has literally 15, like X, Y, Z, A, B, C, freaking axes. Then we really want to reduce the dimensions there. So we'll use something called a PCA, and then we'll graph it after we look at it that way. Now, remember that's going to reduce the amount of things you're seeing, and you won't see the full picture, but it can at least give you a sense of how certain variables are related. And finally, if you're not just value, I don't know, you're probably screwed in a lot more ways if you run into other problems here. But this is just a nice little high-level overview. If you are doing this stuff and you run into a wall, like go to Twitter or Reddit or talk to machine learning researchers, because they're the ones that do this every day, or data scientists. I say data scientists and machine learning researchers interchangeably. I know they're probably not interchangeable, but I use them. So there's other alternatives to Scikit-Learn. So TensorFlow we talked about. Keras is another one. I think someone gave a talk here earlier this month or last month. Theonos is another neural network library. And then if you want to do facial detection and computer vision related algorithms, then look up OpenCV, and that's called open computer vision. So we can do some of that stuff in Scikit-Learn, just a little bit, but if you want to do more, then you can check out that. Okay, so now it's time to actually run some of this stuff. So I have three, I'm just going to do classification because there's literally like full day tutorials in Scikit-Learn at Icon and other conferences. So we'll show you three increasingly complex Scikit-Learn examples and kind of walk through the code there. And the code's already written, and it's in an IPython notebook, so we'll just take our time walking through step by step and show you what it does. So let's see. So I'm going to be using Anaconda. I should already have this launched. Okay. So I'm going to go to my library, and this is called a Jupyter Notebook. And Jupyter Notebooks are, anyone used them before?
Yeah.
Okay, cool. Most people, yeah. So this stuff is unimportant. I'm just importing matplotlib. But here, let's start right here in this block here. So first of all, when you import it, you're going to import from Scikit-Learn. That's the module in Scikit-Learn. And it has a module called datasets, and datasets is a bunch of pre-existing datasets in addition to these functions that make toy datasets for you. So when I talk about getting your data in terms of features and labels, you often see that in Python machine learning code where it, for instance, X and Y. So what this function will do is give us, first of all, let me clear all output. There we go. Okay. So we get we get a bunch of features and a bunch of labels. And then we have to have this little dictionary or this list to reference them. And then what we'll do is we'll take a certain amount of labels from it as well here and print that out. So let's do that. And that's because I did not do this. So it's iterative, so you have to define each one. Okay, so we can see here that this is our these are our features, and for each of these features, the labels are below. So it's just making blobs, and if we graph that, well, first of all, you can print out with NumPy the shape of the data. So this means it's a two-dimensional array. The X value is a two-dimensional array with 1,000 rows and 2 columns, and then Y is a vector of 1,000 elements. So those are all the labels for that data. And then because it's NumPy, you can access them really clearly. So if we play that, I think I'm going to have to keep scrolling up. 1 second. Does anybody know exactly how to do what the keyboard is to run in Jupyter? Oh, here we go.
Yeah.
Command Enter, yeah. There we go. Things via lists, via indices. So we got the first 5 rows here. All kinds of ways to manipulate your data. If you've used NumPy, it's familiar to you, but we don't have to worry about that too much. And finally, we can plot it with matplotlib. So let's do that. And here we go. It just plotted in line, and it shows us that we have the red and blue labels, and we have a bunch of dots scattered around. So this is great. That's kind of how you work with data in Python with NumPy. But what if we actually want to start using real data? So first thing we're going to do is we're going to use a data set from Scikit-Learn that is the breast cancer data set. Essentially, it's a grouping of features of malignant or benign tumors, and then it has the actual labels as to whether this set of features defines that tumor as benign or malignant. So if we want to print this out and look at what it looks like, then we can see here that our 2 labels are malignant and benign. And then all of the features are all of these values right here. So the radius, the smoothness of the tumor, the error of the radius, all kinds of things, the texture, all kinds of values that they package up for you already that say, hey, these are different features we can use. And then here's the actual number values themselves right here. So our goal with this classifier, and it's the naive-Bayes classifier that we use Bayes' theorem to predict whether something is benign or malignant, is to say, given some set of numbers, how accurate are we at predicting whether this tumor is actually bad or good? So first thing we'll do is here, we will, like I said, split up our data into training and testing. We don't want to test our data. We don't want to test our data with the training data. We want to use testing data that hasn't been seen. So we'll first split our data into training and test and the labels for each. I said that initialize the classifier step, that happens right here. We initialize our Gaussian IA-based classifier. When I talked about the fitting step, that's this right here. You do the classifier.fit in a train, and you pass it the features and basically the answers for those features. And every single classifier in Scikit-Learn has this interface, and pretty much most of the regressors. So it's not really confusing. If you pick a new name, pick a new model, it's going to be initialize, pass parameters if you want to, and then fit it, and then finally predict. So let's actually print this out. OK, great. So we fit the data, and then finally we predicted on the test data we passed it. But what if we want to print out the test data? So this says for each of these, this goes on, but for each of these groupings of features that match up with here, that it is either, let's see, malignant as 0 or benign. So it predicts all of those and says for all these groupings of features, what does it think it is? And if we actually print out our score here, we can call a function called accuracy score, and that's built into Scikit-Learn. And that says we're actually 94% accurate at predicting just using a very dumb classifier in Scikit-Learn. If you're familiar with Bayes' theorem, it's very straightforward, and it's just finding a probability based on two other probabilities. So that's probably one of the more simpler examples. You can see with just looks like 7 or 8 lines of code, we're able to classify whether some very important problem could be solved using a computer, given we had data. And this is why I was saying medical issues specifically are a good thing for computers to look at and enhance doctors, because they can reason about numbers that you look at right here that at least I would think would be hard when you have millions of samples of that. How do you actually predict something with it? But a computer sees all this at once and doesn't have to spend days thinking about it. So does that make sense using this? It's pretty straightforward, and you can get started with this now. And actually, if we go to Scikit-Learn's docs, we'll take a look at here for a second. The first thing to notice is that it has the first page is classification, regression, clustering, dimensionality reduction, all of that. And you can actually click on the examples. Kinds of examples here. So for example, I mentioned that eigenfaces data set. So this has it looks at the picture and says it predicted that it was George Bush, and it was true. The model said it was actually George Bush. This one said it was Colin Powell, and it was actually true. And that was based on these eigenfaces every year. And it just shows you the exact code that they used to do it. And I talked about the use principal component analysis. They are doing that right here to get to reduce the dimensions of the data. So in the docs are amazing. They show you how to do all this already. Where I was getting at was if you go to the documentation and look up the data sets module, then let's see, where's just a generic one. Scikit-Learn data sets package. So here we go. So here's some more data sets. So they have Boston House Prizes data set, the Iris Flower data set, if you've ever done machine learning. They have a data set in diabetes, breast cancer, wine, the handwritten digits, all kinds of stuff. And those are already built in for you to mess around a bit with Scikit-Learn. Let's go back and let's do a little bit more complicated example. So the next one is we want to classify handwritten digits. So given a computer looking at pixel values for digits 0 through 9, can we predict based on another picture that it hasn't seen whether that's 0 through 9? So for this one, we're going to use a support vector machine, and that's also going to be a classifier. And if we want to look at the support vector machine and see what it is, then we'll go here, SVM, just click on support vector machine. That it's a set of learning methods, like I said, can be used for classification, regression, and anomaly detection. And it shows you all the data here. And it tells you, each one will tell you what it's good for and what it's not good at. So for example, SVMs aren't very good at, it says here, if the number of features is much greater than the number of samples, then you have to avoid overfitting by choosing a different kernel. So that's something to keep in mind and good to read as you go through this. And the documentation is very, very thorough. So we'll go back and we'll try and predict some handwritten digits. So all this is going to do is load up our data set right here. Zoom in a bit. Okay. Load the data set up and then plot the training digits. So let's do that first. Let's see. Sweet. So we know that for training, this is a 0, this is a 1, this is a 2, and this is a 3. And this is what the model is going to be trained on. It will get not only the pixel values here of each picture, but it'll also know that those pixel values represent, whether it's 0 or not. So the next thing we need to do is we need to flatten that image. So we want to flatten it into just the groupings of pixel values. So we want to do that, and it's done there. So we can say we can print out, see how many samples we have. I don't know why it's doing that. Oh, it's just, this is really annoying. So then we can create our classifiers. So again, I talked about the parameters they take. You just pass them into the initializer. That is really annoying. It is just jumping. Okay, so that creates our classifier. And again, they're all just classes in Python. So if you're familiar with initializing classes, that's all they are. And finally, we fit the data. And then what we want to do is actually predict on that data. So here we're going to get what we expect the data to be, and then what we predicted, and we're going to use the predicting function to do that. And then it'll print out a report to say how accurate we were. So it looks like for the precision, we had a 97% precision. Recall and F1 score, which is another statistic. But that's pretty good. Just using the SVM, we were able to get 97%. Methods, so a lot of deep learning methods have done way better on digit data. So if you look into convolutional neural networks, they're way better representing this stuff. But this kind of model has been around for a while now, and it's still very effective at figuring out things. But that's the general process in machine learning research. Is a lot of times it's you look at previous ways of applying models and data, and you either apply it to new data or some new method, or you come up with a brand new method altogether. But just like anything else in computer science, nothing is absolutely brand new, and everything builds off of somebody else. So it's don't get overwhelmed when you're doing stuff like this. People have done it before, and there's always a way. I mean, unless there's some things that aren't a way. If you're trying to solve NP completeness, who knows if there's a way or not. But, and again here, so it saw this image and it predicted it was an 8. It saw that, predicted it was an 8. It saw that, it thought it was a 4, and that it thought it was a 9. So it was pretty close, and overall, it only missed 3. So that shows using 2 basic classifiers, so the naive Bayes and a SVM. And the last one I'll show before we wrap up is using ensemble methods. So ensemble methods are essentially when you take a bunch of classifiers and you get all of their predictions, and you take the most, like the highest one from all of them. So the one that was predicted the most between all of them. So this is definitely the most complex example, and all we're doing here is we are generating some data using the same function we did before. So it's actually using the iris data. So the flowers. So basically the iris data is you're given a bunch of flowers and you're going to predict like the length of the stems and the length of the leaves and things like that. And all this is going to print out is a graph showing us how different ensemble methods classify the points. So I'm not really going to get into this too much other than show the final result. But essentially here, this is interesting because instead of doing one at a time, we're building a list of all of our classifiers and initializing them together. And then what we're doing is iterating over each of the models and training it and fitting it and getting the predictions. And remember when we talked about transforming the data? That's some of the stuff they're doing here. So there's, they're standardizing the data, so they're getting the mean for it, and they're getting the standard deviation, and they're getting their refined x value, the features based on that. And so at the end, they're doing the prediction down here, and then doing the graph. But this is actually from the Scikit-Learn site, so we won't really talk about too much. Other than I'll show you what the methods are like. Predicting.
It says the decision tree has a 92% accuracy, random forest 92%, AWS is 83. The AWS with more estimators and features the feature 0 and 2 has a score of 99%. And if we look at this right here, then we can see that these are each row is a new type of data we're predicting on. You can see how the points are separate, but it's showing how it predicted that for the yellow points, that decision tree was pretty good about grouping up where it was. Red almost totally encapsulated it. Blue, it's pretty okay. But if we go down to AWS, it was even better. So you can see here, yellow, it nearly got all in its spots, and red. Does that make sense? It's essentially taking those points and looking at what they are and putting its mapping behind it. So the AWS was able to say the blues should be in these blue little shaded areas. And it did this using methods by taking a bunch of essentially trees and saying, hey, what is your decision across all of your trees? And if 10 people voted for red and only 11 voted for yellow, then we're going to vote for yellow for that specific point because more of you voted for that than for red. So does that roughly make sense? So yeah, so that's the brief demo that I was going to show, and again, just showing the documentation. Nothing is better than just looking through this. If I can get back to the home. Well, that's going on. Okay, so again, they have a lot of great stuff here, and installation is very simple. You just use pip for Python, init install NumPy, and anything else you need. So let's get back to the slides, and we'll end with questions. So last thing, takeaways. So Python's explicitness makes it pretty easy to do machine learning. It makes it a lot of fun as well because you don't have to worry about a lot of painful bugs that you encounter in C and C++ and other languages. And Scikit-Learn makes it even easier because it just builds on Python and it exposes very straightforward APIs to doing it. And again, you don't have to have a PhD or math degree in machine learning. You do if you want to be a really, really good one, but you can do this kind of stuff and apply it to your work and your jobs and impress people without it. So, and talk to those people if you want to really know how it all works, because I've worked with a bunch of them at UT and Oak Ridge, and very, very smart. I don't know what else. I don't know. I would go crazy if I was in school for 12 years doing math degree stuff. They obviously didn't. So that's how you can find me. I'm all over the place. And with that, is there any other questions I can answer? Okay. Yes.
Diffusion model you can so what we can handle
Yeah, so if it's trained on enough pictures of, let's say, cats or dogs, then it will. If it's a good classifier, it will say that's neither one. If you have a category for that. So imagine you train your classifier on pictures of cats, dogs, and all kinds of other stuff. So then all kinds of other stuff is what it would fall into. But if you only trained your classifier on 10 dogs and 5 cats, and 5 of those dogs look like pigs, then it might tell you it was a pig. So it just depends on the model itself.
if I want to identify one species, which model are we using? Best, which model is best?
If you're doing what?
I just identify one species and such as one animal or all other animals.
Oh, if you just train it on one animal?
Yeah.
Yeah, so it would hopefully be very good at just picking out that one animal from all kinds of other stuff. So I can't tell you exactly what, it depends very much on the model you're using.
No.
Yeah, it depends what model you're using. I mean, some are better than others, some are, yeah, I can't give you a straightforward example of that. I mean, you can try it if you want. So, does anyone have a better explanation?
And,
Yeah.
and some, I don't recognize one animal.
so it depends very much, but if you, I can't give you a straightforward answer other than the more is better. Always. More is always better, absolutely, yeah. So the more data you have, the more things your computer is able to pick out and can see. So
is there no exactly number?
It very much depends, yeah. So for example, it depends on the complexity of the task too. If you just want to train it to, so a good, very classic example is whether you want to XOR a number. So if you have, remember XOR is just a circuit that says 1 or 0, and whether if it's 1 and 0, then I'll flip it. Then that's a very simple problem because it's very simple features. But if you want to train a computer to drive around a neighborhood and you only give it video and you drive for 2 hours, that's a very simple example, but it's probably going to crash because it hasn't seen nearly enough data to figure out how to turn and avoid people and all that kind of stuff.
Yeah. I have a project about the food recognize. The sample is very, very difficult
To collect, yeah, that's the other thing. So more modern things like deep learning, for example, work not only, but they work very, very well with lots of data. And if you don't have lots of data, they're not very good. Some are different than others, but it just very much depends on what your model is. But again, the more data you have, the better. Yeah, I know that's hard. Like I said, I've had plenty of things where I wanted to solve some cool problem and I didn't have data and I couldn't do it because I don't have data.
Yeah, my boss told me, you must tell me the exact number of you want because the sample is very expensive.
Tell them you want as much as you can get. That's all I thought. Yeah.
And then you split that data between
Yes,
learning and test.
Yeah, so like I showed you there, you want to so say you have 100 samples, there's something called cross-validation where you would split the data a number of times and do it over and over again. Yeah. So it's like k-fold cross-validation. So say you want to split 70% training and 30% testing. Mm-hmm. And then that's how you say, you train on 70%, so then your algorithm tests to see if it can do the same on 30% new data. And then it gives you always want to use the accuracy on the testing data because that's the really the real one. Yeah. Is this like a physics related project or like biology or chemistry?
It's about the wood recognition.
Okay.
I want to classification the wood by the macro. Macro code. From let me check what.
No worries. Yeah, I would just tell him to get as much as he can, but I understand that's probably a hard problem.
For computer vision that you can do, and I don't know exactly what's available, but you can use pre-trained models for similar problems, and then use them. So, if I already have a model, so I'm sure there's a pre-trained CNN out there that can recognize a bear, right? And let's say that you're very interested in a very specific kind of bear, you would need less samples of pictures of, I don't know, a black bear, right? Or a polar bear for it to learn this is black bear, this is polar bear, if it already knows bear, right? So I don't know if somebody's made a wood grain or wood, and then something that would recognize wood.
I use the magnify picture.
Yeah, so probably not. But you never know. I mean, there could be people that are working on something of magnified pictures of cells generally. So if you have something that already can identify, this is an animal cell, this is a plant cell, then you still have a huge leg up. You would need less.
Yeah, my boss will only want to identify one spatial food. It can identify by the eyes. By the eyes. But what I want to identify is the but the sample is very, very expensive.
Yeah.
Very, one sample almost sold. It's very expensive.
So there are classifiers that are better at smaller amounts of data, right? Small amounts of data, right?
Small range.
Yeah, I mean, if you're only working within a set of wood, right, so it's all going to be pictures of wood, then you wouldn't need to have, you also still wouldn't use many samples. Because it's a less complex task, right? Then like, if you were trying to recognize like a tree that has a kind of specific kind of wood from pictures of trees in the woods, right, or something like that. Also, so wait, if you get a sample of wood and you're taking microscopic pictures,
No. The wood is expensive. Every sample is little. It's a little.
applicable compared to like, because if you can fit 1,000,
Yeah.
if your image size is 1,000,
I have separated the sample, separated into many small samples.
right?
But still,
But it's
everything is
expensive.
messy.
Okay.
Yeah.
I mean,
And I see some classification about the face recognition. But the result is very better. It can recognize the people, or recognize this is not a face.
Right.
But to recognize this is not a wood, or this is not this sample, this sample.
yeah, so it's more difficult because for the face ones, it's very good at understanding what a face is, right? And how to differentiate faces. Like when you're showing the arcane faces, the origins are simplified. So if you start with an information, you only need a little bit more information to distinguish a new face. So yeah, I mean, I still think there's probably I don't know. I mean, I don't know what the differences, like how
Maybe-
subtle the differences are of wood at a cellular level.
Maybe you can use Google Maps Street View and pick out the trees in their pictures and see, is that big enough?
I mean, yeah, I'm sure there's a way to do it. I'm sure that, I mean, also the thing you have to think about is, I'm not this, you take thousands of samples
Thousands.
of other wood, right, of cheaper wood and use that to train something up. And then you're going to invest the time. So that, I mean, you can still use the same.
Yeah, actually, the cheaper woods, right, to do some tests.
Right, because so,
That's good. Yes.
Are there any, we can defer this conversation.
Yeah.
After. If there's other questions, they're probably, we good?
When you're looking at faces, like, are you, like, what are the, I guess, parameters? Is it like the geometry that you're looking at, just like a dark area, like for the eyes, or maybe like, you know, it's a match of like, I mean, I'm trying to understand what your classifiers are with parameters that are relevant to identifying a face and how that would transfer to, I'm assuming that you're looking at the, like the grain structure or the cellulose in the like microscopic view of wood, and it may have a certain like geometric pattern depending on which, you know, species or type of wood it is. That I'm just, is there like a crossover or similar?